Hi, student. Today we're going to talk about how to do indirect truth tables. Another way to think about these is to think about these as reverse engineering the truth tables. So I want you to think about what reverse engineering is. It is to take apart to see how it is engineered or how something is put together to make it function. Okay, so if we were to reverse engineer how we test for invalidity for arguments, what we would look for is this pattern wherein the premises are all true and the conclusion is false. Okay, so the main operators, the negation here, the if then for the even P, the if then for the G then P, and finally the P by itself as the conclusion we could assume is false. So this is what we're looking for when we're looking at our truth tables. Okay. So remember for this truth table here, and this is our gas or electric example. Okay, so when we look on every single one of these lines, or if we were just focused, we look wherever P is false, we do not find until the very last line that P is false while the premises are all true. So you've got true, true, and true on the very last line for the main operators. Okay, so reverse engineering here would be, instead of starting with all of the possible truth values, we start with the values of the main operators that we're assuming to be invalid. So here at the top, we would put true under the main operators for the premises and false under the main operator for the conclusion. Okay, if P is false, I'm going to fill this in because P equals P. So P would be false there and false here. So here we go. If P is false, then G must be false for the if then to be true. And if P is false, the E must also be false for the if then to be true. And then when we fill in the values of this negated or, we got negated false or false. And false or false is false. The negation of it is true. So here we've just filled in the possible values that we could find. And we found that they worked, right? For when we assume the premises are true and the conclusion is false. So we now have a row on our truth table where the argument is invalid, and we didn't have to do near as much work as we had to by setting up and doing all of the possible values. We've eliminated many of the possible combinations of the truth table because they can't yield the possibility of true premises with a false conclusion. So an indirect truth table is a method wherein for an argument, one assumes the truth of the main operators of the premises and assumes a false conclusion to determine or to demonstrate whether the argument is valid or invalid. For a set of statements, we'd use this same indirect truth table method to determine whether a set of statements are consistent, meaning they can all be true at the same time or not. An indirect truth table is similar to a reductio ad absurdum, which comes from the concept of reducing to absurdity. An absurdity, technically for logic, is a contradiction. So something which is logically false, or for example, P and not P. So which of the following, this is your active learning exercise, so which of the following is a contradiction? When P then Q equals true, and the negation, parentheses, P then Q end parentheses equals true. P equals true while P equals false. A equals true while G equals false. A or B equals false while A or B equals true. Or A if and only if P equals false, while A then B equals true. So when you're testing for invalidity, you're going to write the sentences horizontally with one slash between the premises and a double slash indicating the conclusion. You're going to start with assuming the argument is invalid. So under the main operators, you're going to have true under the main operators for the premises and false for the conclusion. Then you're going to go through and fill in what must be the case given your assumptions. So if there's nothing essentially implied, then you pick sentences with the smallest possible truth value and you build a mini truth table with that proposition. This is creating what would be the rows that one could find with those values if there were one with all true premises and a false conclusion. So when you're looking at all of the possible combinations, when you're trying to figure out where to start, you're going to start with the smallest possible truth values, okay? Or the least possible. So when there's only one possible truth value, it's either, for example, like this, a negated simple proposition. There's only one truth value for that, so you'd start there. Or a simple proposition. A true conjunction. This is because the only possible values is the both conjuncts true. A false disjunction, because the only possible value has both disjuncts false. And also a false conditional. This is false when the antecedent is true and the consequent is false. So this is the first one you want to see if you can start with and if it can lead you into any other values that you can ascertain. The next one would be any biconditional. So biconditionals, if they're true, they have to have the same value, so both true, both false. So this would be a mini truth table with only 2 lines. And if and only if is false if they don't match. So true if and only if false is false, and false if and only if true is false. So biconditional is the next shortest one to tackle. And if you can't do any of those, then try false conjunctions, true conditionals, or true disjunction. If you're not looking at the truth tables here, look up and look at the mini truth tables here. So these give all the possible values for a false conjunction, a true conditional, and a true disjunction. So you set this up as having 3 lines instead of possibly 8 or who knows, 16, 32, could be much longer. And this should hopefully make it shorter. So, active learning exercise. If you start with the smallest assumption of P if and only if Q equals false, how many rows do you need to show all possible combinations of values for the P and the Q? If you start with the smallest assumption as P or Q equals false, how many rows do you need to show all possible combinations of values for P and Q? If you start with the smallest assumption as P and Q equals false, how many rows do you need to show all possible combinations of values for P and Q? If you're not sure, go back and look at these slides and check to see what the answers are. So under whichever main operator you use or you pick, you create a mini truth table indicating how many layers or how many possible rows on a truth table must be completed for an argument to be demonstrated valid. Remember, any line that's completed and has true premises and a false conclusion demonstrates that the argument is invalid. So stop once it's shown it's invalid. Now, if you complete a line, but a contradiction arises, So something contradicts between either what you've assumed and what you've derived, or what you've derived and what you've derived. Go to the next row to see if an invalid instance occurs there. So what you have come across is a valid instance of a row. So for whichever main operator you fixed how many rows there are, if there are, for example, 3 rows, you get a contradiction on the first row, you have to go to the second. If you get a contradiction on the second, you have to go to the third. And if you get a contradiction on the third, then it is invalid. So if a contradiction arises on every line, then the argument is valid. So step 1, you assume invalidity. So here under the main operators, I put false under the main operator for the conclusion and true under the main operators for both premises. Next, you're going to determine the shortest formula to fill in. Now, the shortest formula to fill in here is the false conditional. The slide's going to go on to show the different steps separately so that you have them later, but I'm just going to fill these in and talk you through this step by step. So first we start here, because the only possible values are a false consequent here, Q false, while A is true. Because true, then false is false. So wherever A pops up, I'm going to put true. And wherever Q pops up, I'm going to put false. Because remember, A equals A and Q equals Q. So here we go. So for A, then Q, we got true, then false is false. We got blank or true is true, which is the case. So that doesn't give us any information about N at this time. But here we've got true, then what is true? So what we need here is we need a true disjunct here to be able to go true, then true is true. Because again, our goal is to find a line that's invalid. And if we get contradictions, then it's not invalid, it's valid. So we're trying to get this filled in with possible truth values. So true, then true. So here we would need blank or false is true. So false or false is false, so it's therefore must be true. You can put true there and put true there. So here we have determined that we can fill it in to have a possible truth value. And we double check. We want to make sure that we haven't made a mistake. So we want to double check A equals A and N equals N and Q equals Q. And all these values are determined correctly. Because we have been able to fill this in, this argument is invalid. I'll try to write this out as neatly as I can. Not doing a great job. All right. So remember, once you fill it in, to put your answer right beside it so that you can put your answers in for your practice exercises. Okay, here I'm going to do another one right here for you guys, just to keep showing you how to do these. So for this one, I'm first going to go through the thinking involved. So the very first thing I want to do is I want to put false under my main operator here. And I want to put true under my main operators for my premises. I only have 2 premises, a negated or and a regular or. And then I've got this if and only if. Now, you might wonder why I only have 1 row set up, because I could start here with my false if and only if. Except I have a shorter version to do, which is my true or. So my negated or means that it's true as negated, so it must be false here. And there's only one possibility, therefore, for our P and our D, and that is false and false. So I'm going to fill in D here and B here. Again, we got to have false. I'm going to put B here, false. And that makes negation be true. Okay. So I filled all these in. And now I can either start working on this area in the middle or start working on this end zone. And I'm going to work on the end zone. Okay, so I've got this has to disagree with this. Remember, for our if and only if to be false, F must be F or false, so that this can say false if and only if true. So that gives us false. So false implies false is true, and the negation of false of true is false. So here what I found is false or false, which I've assumed to be true, but I've demonstrated ends up as false. So I get a contradiction here. That means that this argument is valid. There's no way for me to fill this in for all the component parts to get stable values when I assume that it is invalid. Okay, so I'm going to do another puzzle here. This way, again, I'm just showing you how to fill these in. And the very first thing I'm going to do here is set up my rows. I'm going to start with my B or not D, because all of the other ones have longer possibilities. So, or except for the negation C and B, I could have started with that one. But this one only has 3 possibilities. The if and only if has more because it's got a disjunction here, as does the if then here. So we don't want to start with 3 variables. Starting with 2 is complicated enough. So here we're going to just work on filling these in. So I'm going to start here. And here are the possible truth values. Either B or negation D is true or true. D false. It's true or false, making negation D false makes D true. And finally, it could be false or true, making D false there for the negation D. Okay. So I'm going to start with line 1, and hopefully I can fill line 1 in, find an invalid line, and stop. Whenever I find an invalid line with no contradictions, then I've proven that the argument can be invalid, and I stop at that point. So here we got our B is true, and our B is true there, and our D is false here. Okay. So for this, I'm going to start with this negation C and B. For this has to be a false conjunction because the negation is true. So I'm going to put false right there. That lets us know that C would have to be false in this case. So if we have false, if and only if true, that's false. And therefore, for this to be true, we'd have to have A, B, false. This shouldn't have a row here, but it's okay that it does. An extra row, we'll just ignore it for right now. So next we have our A is false here. Now remember, we're trying to get a false if and only if, and we have C as false. So false or false is false. So false if and only if false is true. So here we have a contradiction. What we've assumed is false for an invalid line is demonstrated to be true under this case. So let's try the next case. The next case has both D and B true. So I'm going to put true here. B is true here. And we got D true here. So when D is true here, this OR is true, no matter the value of C. Okay, and if we want to calculate C, we go back over here again. Because B is assumed to be true, and this is false, C must be false. Now, if C is false, okay, true if and only if false is false. So again, A must be false. And if A is false, false if and only if true, right? Because we can fill C in now, true or false is true. So false if and only if true is false. So we can stop here. This argument is invalid. So that is how you do the indirect truth table method. Usually people like either the truth table method, which takes a little longer but is more rigorous, or they really like this more intuitive method. Okay, so now I want you to practice on your own here. I'm going to walk you through it. So let's first we're going to put down our values under the main operators. We put true under the premises. And false in the conclusion. So we're going to start here with our false conclusion. Our false disjunction only has one possible row of values. What must be the values of C and O? So we're going to put the values of C and O in first. If we know the value of C, does that tell us the value of E? Given E, then C must be true. If we know the value of O, does that give us the value of G? Given G, then O must be true. Finally, now you have both the values of G and E. Calculate the value of G or E. Does it correspond with what we've assumed that this is true? So the assumed value again of G or E is true. So check the calculate value to make sure it does not contradict the assumed value. If it does contradict, then the argument is valid. Is this argument valid or invalid? Okay, you want to stop and screen capture this if you don't have access to the PDFs right now. These are the 4 problems I want you to do using the indirect method to determine if these are valid or invalid. The answers are in your practice exercises. Next, we're going to test for consistency. This is wherein you assume instead of that the conclusion is false, it's more like just the premises. So you assume the entire set is consistent. Consistent means that they are all true at the very same time. So you're going to place the sentences horizontally as on a truth table, except only one slash between the statements. This way you know you're testing for consistency. Here you assume that all the sentences are consistent, meaning they're all true under the main operator for each sentence. So I'm going to show you when I come back to this how to do this. I'm just going to go through the rules very quickly because they're the exact same rules and the exact same guidelines I give you for testing for invalidity. The only difference is that you assume they're all true. So if there's nothing essentially implied, then you pick the sentence with the smallest possible truth value. Avoid any sentence with 3 or more propositions. Under whichever main operator you pick, create a mini truth table indicating how many layers or rows must be completed for the sentences to be demonstrated to be consistent. Here again is the order to fill the values in. Okay. For each of these, for an active learning exercise, I want you to do the mini truth tables for all of the possible combinations that have not been done. So remember, I did these for the invalid. I want you to do the practice mini truth tables, right? For, here we've got false conjunction, true conditional, true disjunction, and the 2 types of biconditionals. This is to get you, if you have not memorized them, to finally memorize, because for these, you need to have them in your mind to be able to intuitively leap to the next one. So under whichever main operator you pick, create a mini truth table indicating how many rows must be completed for an argument to be demonstrated. Sorry, it's this argument. First sentence is to be demonstrated as consistent. Remember, any row that's completed and has true under the main operator for each and every statement is consistent. Stop once it's shown to be consistent. If you complete a line but a contradiction arises, P and not P, then you must go on to the next line to see if an instance of consistency occurs there. You must continue this process until all lines are complete. If a contradiction arises on every line, then the set of statements is inconsistent. Okay, so now we're going to go back and I'm going to show you how to do this. Again, we're testing for consistency here. And it's easy to get these, to forget which one you're doing. So do these at separate times to make sure you don't confuse them. So here we go. Under the main operators for this, we're going to put true under all of these. Okay, so true, true. We've got 3 true if-thens and 1 true disjunct. And I've got a true, a negated if-then that's true. So here we go. We're going to practice with this one. We're going to start here because this inside, this if-then must be false, which means that H, the antecedent, must be true, and negation E must be false, so that E must be true as well. Okay? So now I'm going to fill in E. E is negation, E is false there. And negation H is false there. And H is true here. Okay. So here we have a really good setup wherein we don't know C or D's value at all, but it doesn't matter because we have a false antecedent. And we have a false antecedent here, so this is true already. And we have a false antecedent here, so this is also true. So all we have to do is get our B, and also this is true because B then H is B that is blank, then true, which is always true. So we don't need to determine B's value either. What we do need to do is to make this right here work. So I'm going to assume C is false and assume D is true. So that gives us a true and true on a line. We can go back and fill that in. And we'll just do a true here. So here we go. True then true is true. True or true is true. False then true is true. False then true is still true. And the negation of false is true. So here we have a line in which they are consistent. So these are consistent. I'm not going to write the whole thing out this time. Okay. So here we're going to practice. I'm going to show you 2 more examples before I have you working on your own again. So for this one, we're going to go true, 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 true. Now this one has a true conjunction, which is a blessing. That means that we know the value of H must be true and negation E must be true. So E must be false. So E doesn't pop again, but H sure does. So H pops here, which does not give us any value for our D, but it does allow us to have a true if-then. And H is true there. Now that tells us that C must be true. Because true then true is true. So C is true, so the negation of C must be false. False or blank is true. So false or true is true. So here we have it all filled in, and we have a set of consistent sentences. There we go. So these are also consistent. Okay. The last one I'm going to do for you, I'm going to show you just to make sure you know how to do this, how to set it up. Under your main operators here, we've got an or, and we've got an if then. All of these are assumed true, so we've got to pick one of these to fill in. So I'm going to let you do this as I am doing this. And I can't ask you which one you're picking. So I'm going to pick one at random. I'm going to pick the first one. So C or F. Also, C is here and F is here, so they're all well spread out. So here we go. True or true? True or false? False and true. I always set up the one I'm starting with to make sure that I check everything. So here we go. So C is true, so negation C is false, which means G must be true. Now, negation F is true, so negation F is false. But we've already assigned G as true, and true then false is false. So here we have a contradiction that arises on our first line. So let's see if we can get it to work on the second line. On this one, we got C or F. So again, our C is true. So our negation C makes it false. So G must be true. So G is true. And for this one, F is false. So negation F is true. And here we've got true, then true is true. So wherein it did not work on the first line, it works on the second line. So these are also consistent. Okay, now stop and screenshot this or get the questions from your PDF. These are your practice problems for testing statements as consistent or not. Remember, what is the key difference between testing for consistent sets and testing for argument? So this is what you learned this lesson, how to construct indirect truth tables for both validity and invalidity, and consistency and inconsistency.